All right. So in section 5.1 and 5.2, they talk about eigenvectors and eigenvalues. So basically, we have a vector, eigenvector v, and eigenvalue lambda, right? So lambda and v are lambda is a number, of course, and eigenvector is a vector. So they have this relation. Of course, a matrix is given to you, given a matrix n by n matrix, n by n, okay, A. So a vector is called an eigenvector of A if I multiply A with V and it gives you lambda with V. So I get the same vector back basically. You see, the same vector comes back, but with a number. Lambda is a number. So on the left, we are multiplying by a matrix. On the right, we are multiplying by a number. So basically, not all vectors will have the same property. If this is your vector, V, and when I multiplied a matrix A, it gives me the same vector but a little longer or little shorter, right? Because lambda times V is a vector in the same direction. So see, we multiplied a matrix with a vector and it gives me the same thing as a multiple of a vector. If you get some other one, if you multiply, if you have a vector and you multiply, let's say this is another vector, a vector U, and you multiply a matrix and the matrix gives you some other direction. Let's say this is your AU, then you will not be an eigenvector. You see, we got rotated. We are not in the same direction. So this is what we are not looking for. Okay. So anyway, um, if a vector is given and a matrix is given, it's very easy to check whether it's an eigenvector. We can just multiply. I think I did both the things last time, how to find the eigenvector, or if, let's say, if I have to check it. Uh, so here is your, if you look at these, this is the example that I did. If a vector is given and you have to check whether it's an eigenvector, it's not difficult. We can multiply with A. For example, A is 1652 and a vector is given 6 minus 5. If I have to just check if U is an eigenvector of A or not, right? So if I just have to do that, I will just multiply A with U and see what is that. 1652 multiplied by U, 6 minus 5. If you multiply, how you do it? You take the first row with first column. So it gives you 1 into 6 plus 6 into minus 5. And then the second with second, this row with this one, right? So it will give you 5 into 6 plus 2 into minus 5. So now if you write the answer, it gives you 6 minus 30 minus 24, and 30 minus 10 is 20. So see, no matter what you do here, let's see if you get 6 out of it. You have class? I'm taking it. Huh? I'm taking it online. There was no one in the class, so I came here and just started online lecture. Yes. You have something you can. Yes, I want to see my exam at 10 paper. Can you come after the class? In 1 hour, 11:40, 11:50. Okay. Thank you. So if I take 6 common, uh, if I take -4 common, it gives you 6 and -5, right? See, if I take -4 into 6 is 24, and -4 into -5 is 20. So you see, I got a number outside and my vector v comes back. Vector u comes back. Who is here? All right. So our vector u comes back, so it means it is an eigenvector. And v is 3 minus 2. So it means this implies that u is an eigenvector, because when I multiplied a with u, my vector u comes back with a number. So I can say that yes, u is an eigenvector, and this -4 is your eigenvalue, and -4 is the eigenvalue corresponding to u. Okay, so whenever you have an eigenvector, there will be an eigenvalue. So eigenvalue, we can say that corresponding to 4. If you change a vector, another eigenvector, you may get another eigenvalue. Okay, so we call it lambda basically. Lambda is -4. Another vector is given, v, 3 minus 2. And if I have to check whether this is an eigenvector or not. So if I multiply a with v, because there is only one way to check whether something is an eigenvector or not, is that multiply. So 1 into 3 minus 6 to the 12, 15 minus 4. So this is the product. If you, because 1 with 3 and 6 with 2. So 3 minus 12. Then 5 with 3, 15 minus 2 with 2, 4. So you got -9 and 11. So now you see, no matter what you choose a lambda, you will never get your vector back, 3 minus 2. You see, your vector is 3 minus 2. You want to get that back, no matter whatever you choose. So you are not getting this vector back for any choice of lambda. You can try that. If I take lambda -3, -3 into -3 is -9, but -3 into 2 does not give me 11. So you can check anything. So here I can say that V is not an eigenvector of A. Of A. Okay. So it's very easy. If vector is given, it's very easy to check whether it's an eigenvector or not. Multiply matrix with a vector. If your vector comes back with a number, it becomes an eigenvector. Otherwise, it's not an eigenvector. Now, if an eigenvalue is given, can you check? If A is given, let's say A is the same thing, 1652, and they are asking, check whether lambda equal to 7 is an eigenvalue or not. So the same 1652 is given. Now a given lambda, the question is lambda 7 an eigenvalue of A or not? So eigenvector was easy, but eigenvalue is not that easy. An eigenvalue of A? This is another question. So here, because a vector is not given, I have to show that AV is equal to 7V, because eigenvalue is given. So I put the value of lambda. So now the question is, does this system AV or any vector AX is equal to lambda X has a solution or not? If it has a solution, X, this is basically the question. Is lambda 7 eigenvalue? Means ax is equal to 7x has a, if it has a solution, then lambda will be an eigenvalue. So here, if I write ax minus 7x equal to 0. So a is 1652 and x is x1 x2 and minus 7 x is x1 x2 equal to 0 0. So if you write a system here, it becomes 1 x1 plus 6x2 and 5x1 plus 2x2, and then you subtract minus 7x1, here you subtract minus 7x2. So this is your vector equal to 0 0. So it means your system becomes minus 6x1 plus 6x2 equal to 0, the first one, and the second one is minus 7 is minus 5x2. This is your system, right? If this is your system, you have to, and both equations are the same from here, you see. Both equation gives you x1 equal to x2, right? And x2 is free. So it means I have a solution. So this implies that a x equal to 7x has a solution. And this means that lambda is equal to 7 is an eigenvalue. If this system has no solution, then lambda will not become the eigenvalue. So yes, this is an eigenvalue of A. And from here, you can also write the augmented matrix. If a vector. If I write x, x is x1, x2. x2, x1 is x2, x2 is free. So if I take x2 common, it is 1, 1. So I don't want any multiple. You see, I want a vector. Now, if you take different values of these x2, it will just make it longer or shorter. That's it. So you can pick just this one. You can just pick this one. This 1, 1, it gives you the direction. So this is the corresponding eigenvector. So from here, I can take 1, 1 is the corresponding eigenvector. Corresponding is an eigenvector corresponding to the eigenvalue. So you can say that this is the eigenvector corresponding to the eigenvalues 7. Corresponding to lambda equal to 7. So you see, when a vector was given, when I proved that this is a vector, u is an eigenvector, so I wrote the corresponding eigenvalue. This is easy. But when I proved that lambda is equal to 7 is an eigenvalue, so I wrote a corresponding eigenvector as well. So of course, whenever you have an eigenvalue, you get a vector. Whenever you have a vector, you get a value. So these two examples, in these two examples, your eigenvalue, eigenvector were given. One of them was given to you. Here the vector was given, here the value was given. Okay. But now, what if both are not even given? So how to find both eigenvalues and eigenvectors? This is the issue. If nothing is given to me, only a matrix will be given. Eigenvectors. Okay, this is the main question now. Only given a matrix A, given a square matrix A. That's it. This is only given to you. Nothing else is given. So let's see, I had open something, open the notes that are given in the Moodle. So I can pick the same thing. Let's say this is the same example you see written here. 1652. Okay, it is the same example. So I can do this one. 233 minus 6. Okay, so now if this is the only given matrix, I have to find lambda and v, right? Where for lambda and x, you can say that where ax equal to lambda x. Basically, this is what we are looking for. We are looking for lambda and x from one equation. So see, there are two unknowns in one equation. Now it's difficult. If one of them is given, I can find the other one. If both are not given, we are in trouble. But let's see what I can do. So if ax is lambda x, then ax minus lambda x is equal to 0, right? I can bring it to the left side. If I take x as common, x is common, so I can write a minus lambda x equal to 0. But the problem is this cannot be done. A is a matrix, right? And lambda is a number. How can I subtract a number from a matrix? It is not possible, right? A minus lambda is not possible. I can multiply a number with a matrix, but I cannot add or subtract a number from a matrix. It means I need something more here. So see here, if I write this x as identity into x, there is no problem, right? Because identity into x is x. Identity multiplies by any vector, does not change it. So now I can write ax minus lambda ix equal to 0. We can do that. Now if I take x as common, it is a minus lambda I. Now there is no issues. This is a matrix. A minus lambda I is a matrix, no issues with that. So this can be done. Okay. And what is A minus lambda I? You see, I is 1011, right? 1001. So this will become lambda 00 lambda. So lambda I is a matrix who has lambda on the diagonal. That's it. If I have A as, let's say, A, B, C, D, and lambda I has become lambda 00 lambda, then A minus lambda I becomes A minus lambda, B minus 0, C minus 0, and D minus lambda. It means I just subtracted lambda from the diagonal. You see, if you look at that, I just subtracted lambda from the diagonal. If A minus lambda I is written, just subtract lambda from the diagonal. That's it. Off diagonal elements don't change. Okay. So how we got this matrix? By subtracting lambda from diagonal entries. That's it. Lambda from diagonal entries. Subtract lambda from diagonal entries and you get these directly. You don't have to write these both and do that. Just subtract lambda from the diagonal. But anyway, coming back to this equation, when this will have a solution, you see, uh, this always have a solution 0. Always have a, this system always have a 0 solution, right? That is x equal to 0. But 0 is not an eigenvector. We are looking for non-trivial solution, non-zero solution. 0 cannot be an eigenvector. Remember that. We are looking for non-zero solution, x. Okay. So if x is not equal to 0, it means we are looking for non-trivial solution. So a homogeneous system, if you recall from your previous chapters, a homogeneous system, this is the homogeneous system, right hand side is 0. A homogeneous system let's write it bx equal to 0 has non-trivial solution only if has non-trivial means x not equal to 0 solution only if B is non-invertible. Means if the inverse of B does not exist. Why? Because if B inverse exists, then I can write the solution. I can just multiply B on the right, B inverse on the right, multiplied by 0 gives you 0 solution. Okay, if B inverse exists, then 0 is the only solution, and I don't want it. Hence, so this implies that for non-trivial solution, B inverse should not exist. So this implies for non-zero solutions, B inverse should not exist. Okay, I should not have the inverse of B. And what does that mean? It means determinant of B must be 0. You know that when the determinant of a matrix is 0, then B is non-invertible. So this is what I want, right? This is what I want from here to here. This is aside. This is an aside note. So what was my system? My system was this one. Okay. So this will have a non-zero solution if, so hence for non-zero solutions of my system, which is a minus lambda I x equal to 0, we need determinant. We need a minus lambda I to be non-invertible. So we need determinant of a minus lambda I to be equal to 0. This is the first condition. Okay. And this is, if you solve this one, if you take the determinant of this one, it will give you a polynomial in lambda. It is a polynomial equation in lambda. Okay. Which is called a characteristic equation. This equation has a name. It is called characteristic equation. So basically, and here you see there is no x, there is only lambda here. You see, only lambda is here, no x is here. So it means it will give me only the eigenvalues. So solving this equation, we will get eigenvalues lambda. So it means first I will get the eigenvalues of the matrix A. And then I know that if an eigenvalue is given to me, I can use that eigenvalue to solve, right? Then for every lambda given, right? Because we got the eigenvalues lambda, right? So for every given eigenvalue lambda, we will solve a minus lambda I x, solve the system, the old system which we had here, this system. I will solve this one because lambda is not unknown now. I will solve this to get the eigenvectors. So this is our criteria now. Of course, I did all this to make sense of what we want to do. But now, if a matrix is given to me, I will directly start with the characteristic equation. So let's say I can start with a 2 by 2 matrix, 2, 3, 3 minus 6. And the question is 2, 3, 3 minus 6. So question is find eigenvalues and eigenvectors. Find eigenvalues of A, find eigenvectors of A, right? So we can do one by one. So I will start for eigenvalues. Let's say this is question A, this is question B. Okay, so for A, for eigenvalues, I will solve the characteristic equation A minus lambda I equal to 0 for lambda. There is no x here. It's a polynomial equation. So what was A minus lambda? So determinant of A minus lambda. I said just subtract lambda from the diagonal. Or let me write a minus lambda first. So let me first write what is a minus lambda. A minus lambda is subtracting lambda from the diagonal. 2 minus lambda, 3, 3, and minus 6 minus lambda. Now, if I find the determinant of a minus lambda I and put it equal to 0, it means I need the determinant of 2 minus lambda, 3, 3 minus 6 minus lambda equal to 0. And now how we find the determinant? We multiply these two. So 2 minus lambda into minus 6 minus lambda, and then multiply these two. And minus 3 into 3 is 9 equal to 0. Now I can multiply 2 with 6, 2 with lambda. So I got minus 12 plus 2 lambda, and then lambda with 6 and lambda with this. So plus 6 lambda plus lambda square minus 9 equal to 0. So see here what I got. If I write, okay, let's write it here. So lambda square 6 plus 2, 8 lambda, and minus 12 minus 9 is minus 21. This is minus 2 lambda. I don't know why I write plus. This is minus 2 lambda. When 2 gets multiplied by minus lambda, it's minus 2 lambda. So this is 4 lambda. Okay. Now I have to make factors. So lambda and lambda equal to 0. So see lambda 7 into 3. I need product. I need product to be 21. So 7 into 3, 7 into minus 3 or minus 7 into 3. These both give you 21, right? But if I add, I need plus 4. So it means I will pick these two. If I add them, it's plus 4. So 7, lambda minus 3 and lambda plus 7. Right? So now from here, I will get lambda equal to 3 and lambda equal to minus 7. So see, you got two eigenvalues. Of course, if A is 2 by 2, we get two eigenvalues. Okay. If that is 1 by 1, I will, sorry, 3 by 3, I'll get three eigenvalues and so on. There is one, why I go over there all the time. Here you see, if you add the diagonal elements, okay, I'll tell you later. Anyway, now to find eigenvectors, I need one by one. Okay. Now to find eigenvectors, I will start with 3. So for lambda equal to 3, I will solve a minus 3i because lambda 3 is given into x equal to 0. Right. So I will put lambda in my equation a minus 3ix, and I will solve this for x now, for the vector x. So this is a linear system. If it is a system, I can write the augmented matrix, right? A minus 3i. And if you want, you can write 0, 0 as well. But we can just write the matrix on the left. So 2 minus 3, 3, 3, and minus 6 minus 3. And again, you see, I subtracted 3 from the diagonal, right? You see, a minus 3 means subtract 3 from the diagonal. That's it. Okay. So this gives you a minus 1, 3, and 3 minus 9. Now I can use row reduction algorithm. So I can multiply R1 with minus 1. So it will give me 1 minus 3, 3, 9. And now I can use this 1 to make this 0. So R2 minus 3 R1. So if I do that, 3 into this. So see here, I multiply this by minus 3 and add here. So minus 3 plus 3 gives me 0. And Minus 3 into minus 3 is 9, and 9 plus 9 gives me 0. Of course, one of the row has to become 0, otherwise you don't get non-trivial solution. At least one row will always become 0 here. At least one row. If it's a 3 by 3 matrix, maybe two rows become 0. We don't know that. So at least one row becomes 0. Otherwise, you will not get a non-trivial solution. Okay, remember that. So now if you write the solution, it is x1 plus 3x2 equal to 0. So this means that x1 is equal to minus 3x2 and x2 is free, right? I did not get. So one of the variables should be free. So therefore, my vector x becomes x1, x2. You see, we studied in 1.5 how to write a vector form of the solution. So we write x1, x2, and then we take x2 as common. So we got minus 3 into 1. And when we get this, I only pick this one. We only pick this one for the vector, and we call it v1. So therefore, v1, the first eigenvector, which is minus 3, 1, is the eigenvector for lambda equal to 3. And I can call lambda 1 is an eigenvector. Sorry, is an eigenvector for lambda equal to 3. So I called it lambda 1. So lambda 1 v1 is one eigenvector. But I have the second one as well, lambda equal to minus 7. So now I can consider lambda equal to minus 7. So for lambda minus 7, I will solve a minus minus 7i x equal to 0 for a new x now. This is a new x here now, not the old one. Okay, new x here, or you can write y if you want. So now this is a plus lambda I, a plus lambda I. So now I will just write a plus lambda 7 lambda I. So 2 plus 7, 3, 3 minus 6 plus 7. Right now I am adding 7. I am adding 7 in the diagonal entries only. So if you do that, it is 9, 3, 3, 9. So you can divide R1 by 9. You will get 1, 1 by 3, 3, 9. Now the same, multiply this by minus 3 and add here. So you will get, so I can write this as R2 minus 3R1. It is a coincidence that you are getting the same thing back. Otherwise, these operations can be different. So 1, 1 by 3, when you multiply by minus 3 plus 3 gives you 0. When you multiply minus 3 with this 3 gives you 1, and 1 plus 9 is 10. So this is wrong. There should not be 10. One of the rows has to become 0. You see, one of the rows should become 0. So this should be 0, not 10. So something is wrong. So let me check again. A plus 7, I, 2 plus 7, 3, 3 minus 6 plus 7. This is a mistake. Let me write it in blue now. Minus 6 plus 7 is 1, not 9. I don't know why I wrote it 9. Okay. So this is 1. Now you see, if you multiply this with 3 and add here, it will become 0 and 0. So one of the rows have to become 0. So now we are okay. So now if I write my solution, now my solution is x1 plus 1 by 3 x2 equal to 0. So from here, I can write x1 equal to minus 1 by 3 x2, and x2 is free, right? So therefore, my vector x has become x1, x2. X1 is 1 by 3 and x2 is 1. So minus 1 by 3, x2, and x2 is x2. So now if I take x2 common, you have -1 by 3 and 1. Usually we don't like -1 by 3. So if I multiply 3 inside, or if I take x3 by 3 outside, you will get -1 and 3. So it's better because both vectors will give you the same direction. You see, -1 by 3, 1 is this vector, -1 by 3, 1. And -1, 3 is a little longer vector. That's it. Direction is the same. So avoid fractions. If you can do avoid fractions, take this as a second eigenvector. So from here, you can say that my second eigenvector V2 is -1, 3. If you take this as the second eigenvector, the answer will be correct. -1 by 3, 1 is also a correct answer. Okay, is the eigenvector corresponding to lambda equal to 7. So this is the eigenvector for the second eigenvalue, lambda 2 equal to -7. So now you see I got two eigenvalues and two eigenvectors for the so I think I got the same. Yes, the first eigenvector is 3, 1, the second is -1, 3. Okay, so it is the same thing. So every time I go there. So I think that's pretty much it here. Yeah, the note that I was trying to tell you, it is a small check, but if you add eigenvalues, sum of eigenvalues and sum of diagonal entries are always equal. Sum of diagonal entries, they are always equal. So if you have a mistake, you may check it from here, but this does not confirm your answer is correct or not. Maybe you get a wrong eigenvalues and the sum is still equal to the sum of diagonal entries. You see, the diagonal entries here were 2 plus -6, right? 2, 3, 3 minus 2 plus -6, and your eigenvalues are 3 plus -7. So see, both are -4. This is -4. This is also -4. See, so this is just one check or remark. You can maybe, if you get a wrong, if you don't get these two equal, then you can check your question whether you did the correct solution or not. So sum of eigenvalues means lambda 1 plus lambda 2 plus so on, and equal to diagonal entries a11, a22, a33, and so on. They will always be equal. Okay. So in above example, we can see that the sum of diagonal entries and sum of the eigenvalues are the same. But this does not guarantee that your answer is correct. But at least it will tell you if it is wrong or not, if these two sums are not equal. All right, so I think that's pretty much it. I will continue with the same discussion next time. So only new thing I did today is this how to find both eigenvalues and eigenvectors, right? So this is what I did today. So first you will not, of course, do all these things. I explain, this is what I did to explain you. So whenever you have to find the eigenvalues, eigenvectors, right, you have to follow this example. For eigenvalues, you will directly solve this characteristic equation, which is a polynomial equation. And once you get the eigenvalues, then for each eigenvalues, you will solve this homogeneous linear system. So solving this homogeneous linear system will give you the eigenvectors. All right, guys. So that's it. So we can stop here. If you have any questions, you can ask me. Here. So let me stop the recording first.